So today we're going to take a look at our final value for thermodynamics, Gibbs free energy, or delta G. Sometimes it's also just called free energy. All right, let's think of where we've been so far. So we've talked about enthalpy, right? The measurement of potential energies of bonds. So we've got delta H's. And what we saw is most of the time, equations want to go to a more stable energy state, right? So if our reactants are up here, okay, and the bonds of our products are down here, okay, this is often what happens. The reactants go down to a more stable energy state as products, and then the energy is released as heat. So we've talked about enthalpy. Okay, well, the problem with that is, well, sometimes we see reactions that are the opposite, right? We have a reactants go here and the products go up here. Okay, we have to add energy to that system. And even sometimes these reactions that have a positive or an increase in enthalpy even happen without any outside force or are thermodynamically favorable. So we came up, second term they came up with was this idea of entropy. Right, so entropy, or delta S, or S, is the measurement of disorder, right? So the measurement of disorder, so this idea that things move, or thermodynamically favorable processes always move to an increase in disorder in the universe, right? That idea of, if you take a deck of cards and throw it up in the air, is it possible that it's going to land ace, king suited? Yes, but is it likely? No, because there's so many more other options or permutations available. So the universe is going to move towards disorder, right? But sometimes we see that processes that happen sometimes become more ordered. One of the questions somebody asked the other day was, well, why does why does water freeze, right? Why does water become ice? Because this is a decrease in disorder, right? So even though it's a decrease in disorder, the process still happens. So what we have here on any given time is there's two driving forces that can create or make a reaction happen. Sometimes enthalpy drives a reaction, sometimes entropy drives the reaction, and what we have to do is we have to weigh both of them and determine, okay, well, which one drives the reaction? So how we're going to do that is we're going to look at Gibbs free energy. So Gibbs free energy allows us to look at both enthalpy and entropy and see which one's more important and what's going to happen to the reaction. Okay, sorry I got interrupted, so if it's a little choppy, I think I knew where I was at. So we have to look at both and determine which one is more important. Sometimes enthalpy drives a reaction and overwhelms the entropy or the disorder, and sometimes the increase in disorder is more important than the increase in enthalpy. All right, so Gibbs free energy is going to allow us to look at those two terms. And our equation for Gibbs free energy that we're going to use is delta G, or one of them that we're going to use, is equal to delta H minus T delta S. Okay, and what we see here is there's two terms in here. So we have a term for enthalpy, and we have a term for entropy. Okay, so either one of these terms, and also if you see here, entropy is temperature dependent as well, okay, or is affected by the temperature of a system. Okay, so what we know about delta G, or Gibbs free energy here, or free energy, that is, if the change in free energy is less than 0, okay, the reaction is spontaneous or thermodynamically favorable. So I'm going to use the correct term, TDF, thermodynamically favorable, in the forward direction. Okay, if delta G is greater than 0, that means the reaction is thermodynamically favorable in the reverse direction. And finally, if delta G is equal to 0, the reaction is at equilibrium. Okay? So here's what we'll start today. Now we can start to weigh both enthalpy and entropy into one term, this free energy or Gibbs free energy. All right? And based on the sign of delta G tells me which way the reaction is going to proceed, which way it's going to be more favorable. You know, if you think of it as a ball rolling down a hill, and maybe there's another, like in a valley here. So at first, if the ball is here, it's going to roll down, but it's not going to stop here initially. It's going to do what? It's going to roll back up to here, but then once it's here, it's going to what? Roll back down. Okay? So you have, you know, even within a process sometimes, or a reaction that's reaching equilibrium, you know, sometimes the forward reaction is favored, then the reverse reaction is favored. But eventually we know what? That the ball is going to settle out down here. And this is the minimum free energy. Okay? So processes always want to go to the minimum free energy available, or their free energy or Gibbs free energy is always going to decrease for a thermodynamically favorable process. So the big thing we want to look at this too is when are some things when reactions are always going to be thermodynamically favorable, and when are some times when reactions are never going to be thermodynamically favorable. So if we remember our signs for delta G, so if delta G is less than 0, or I'm just going to say negative here, if delta G is negative, always TDF. If delta G is positive, it's not thermodynamically favorable. Okay? And if delta G is equal to 0, then it's, you know, it's at equilibrium. So let's weigh some stuff. So looking at this reaction, so delta G is equal to delta H minus T delta S. Okay. So let's look at some signs for H and for S and determine some stuff. First off, if delta H is negative, okay, exothermic, okay, the bonds of the products are at a lower energy state than the bonds of the reactants, right, less potential energy. And delta S is positive, or there is an increase in disorder, both of those processes are favorable, right? Products or chemicals want to go to a more stable energy state, and it wants to increase the disorder of the universe. So if delta H is negative and delta S is positive, this is always, or TDF, thermodynamically favorable, at all temperatures. I guess I'm moving my things. I'll just put temp. Thermodynamically favorable at all temperatures. Okay, let's go next. What if delta H is positive? Okay, so this is endothermic reaction. I've got to add energy to the system. And delta S is negative. So there's an increase in disorder. Okay, well, if I have an increase in enthalpy and an increase in disorder, a decrease in disorder, I made a mistake there, and a decrease in disorder, this is not TDF at all temps. Okay? This is not a thermodynamically favorable process at any temperature, right? Because I have to add in energy to the bonds, and it's becoming more ordered, not thermodynamically favorable. Doesn't mean it won't happen. Okay? You can stress a system, or you can add outside energy, and you can make processes happen, but it's not spontaneous or thermodynamically favorable at any temperature. Okay? It's not thermodynamic. Now, let's look at some that sometimes are or sometimes aren't. So if I have a negative delta H, right, exothermic, but a negative delta S, okay, an increase in or decrease in disorder, this is thermodynamically favorable. When this value is greater than this value, right, because I'm minusing a negative or I'm adding in. So in this case, delta H has to be larger than delta S. And when is that going to happen? At low temps. At low temperatures, this reaction would be thermodynamically favorable. Okay, an example of this is when ice freezes, right? Ice freezing, okay, we have a decrease in enthalpy, but we have an increase a decrease in entropy as well, or a decrease in disorder. So the process is becoming more ordered. That's not favorable, but this overweighs that at low temperatures. And we see that ice freezes at 0 degrees Celsius. Well, it doesn't freeze at 5 degrees Celsius. So we would say this reaction or this process is driven by enthalpy. Okay? Now let's look at another one. What if my enthalpy is positive, all right? So my bonds, my reactants, I have to add energy. It's an endothermic process. Bonds of the products are greater than the bonds of reactants, but I also have a increase in disorder, which is favorable. Okay? So this is thermodynamically favorable when delta H is less than negative T delta S, or at high temperatures. Okay, so at high temperatures, even though there's even though I have to add energy to the bonds to get up to the products, the increase in disorder drives that reaction. We would say this is driven by entropy. Driven by entropy. All right. So there is an intro to Gibbs free energy and the things, when reactions are driven and what they're driven by. Okay, you need to be able to understand and conceptualize this right here. What does negative H and what does a positive S tell me? Okay, hey, that's thermodynamically favorable at all temperatures because both of these are favorable. Well, what about a positive negative? It's not thermodynamically favorable because neither of these are favorable. And then at these points down here, it depends on which term is greater. Sometimes it's driven by enthalpy, sometimes it's driven by entropy.